Hello and welcome to this lesson video where we will learn about hauling operations using trucks and their production estimate using deterministic analysis. This video covers the shown three learning objectives. Trucks are designed for a single primary reason, hauling material. This is why it beats scrapers in long-haul distances that usually exceed 1,500 feet. The shorter the haul distance, the more scrapers and dozers become economical. Trucks generally require well-maintained haul roads to operate efficiently. Trucks can be classified based on different factors. Most of the trucks are diesel engines due to their fuel efficiency. These photos show trucks with different number of axles, which is an indication of the weight of the truck can haul. Finally, trucks can dump from the rear, bottom, or side. End dump trucks are the most common trucks, and they are used in cut and fill operations where dumping the soil in piles will be spread later by a dozer or grader. Side dump trucks are specialized trucks when site accessibility prohibits the maneuvering of the end dump trucks, like in roadway construction. Belly dump trucks or trailers are common in mass excavation projects where dumping the soil while the truck moves in layers is more economical than in dumping it in piles. Truck capacity is also called payload, as traditionally earthwork contractors are paid for their work by the number of hauled truck loads. The payload can be either in volume or weight units, but volumetric payloads are more relevant to planning earthwork operations. The volumetric payload is expressed in loose soil volume, and production calculations can assume struck or heaped load depending on the site or off-site hauled constraints. For rough terrains, articulated trucks are versatile due to their pivoted frame design compared to the traditional rigid frame trucks. You can see in the side photo of the articulated truck a pivot, which enables the front and rear parts of the truck to rotate separately and provide a smoother drive over rough haul roads. These trucks are classified as off-road trucks, meaning that they need to be loaded on a trailer to be transported from a site to another. So this is why we see these trucks in only large earth-moving projects. Articulated trucks provide higher speeds on rough roads, but relatively small payloads with respect to their large sizes. So next, we will observe a hauling operation, and you will need to identify the cycle steps, resources, and factors that affect the hauling production. As you have seen in the video, the single whole cycle includes these 5 steps. The excavator loads the truck hauls the material to the dump area, the truck dumps the load, the truck returns to the load area, and the truck spots a loader or excavator and maneuvers to get loaded. We did not model another spot step before the dumping because it is not dependent on another equipment like the excavator and loading. They basically arrive at the fill area, dump, and leave. Also, to agree on some terminology, we can lump uh, all the steps except for loading into a large step called transit and estimate its time to represent the part of the cycle when the truck is away from the loading equipment. If the loading happens in an open area with very smooth maneuvering for the trucks, the spot time can be ignored. Now, estimating the whole production will require estimating each of these 5 cycle steps. The dumping and spot times are arbitrary values that are assumed by the estimator depending on the site conditions. Let's see how the load, haul, and return times can be estimated. The load time calculation depends on the information available. The calculation can be more detailed if the following information is available for the loading equipment. The bucket size, and the loading cycle time. Refer to the excavator lesson to see how the loading cycle time is estimated. First, the top formula calculates the number of trucks needed to fill a whole unit or truck by dividing the whole payload by the truck size or the of the excavator or loader, which both are in loose cubic units. Different fill factors can be applied to the payload and the bucket volumes. If it is assumed that the truck will be fully loaded, then the number of buckets will be rounded up. Otherwise, truck short loads will mean rounding down. Second, the load time is calculated by multiplying the number of load buckets by the time it takes for each bucket to be loaded in the truck, which is called the loading cycle time or the excavator cycle time. If all this data is not available, then the load time can be estimated by just knowing the ideal production of the excavation unit and using the shown formula to calculate the load time. It's recommended to calculate the load time and the other whole cycle step times in minutes for better production calculation accuracy. So be careful with unit adjustments when using the whole unit payload in loose cubic unit and the excavation ideal production in loose cubic units per hour. Haul and return times can be estimated based on the available information. A detailed approach will entail using the performance and retarder charts of the equipment and the whole road grade and rolling resistance data to calculate the haul and return speeds. Afterwards, the haul and return times can be calculated by dividing their distances over the speeds you calculated before. Otherwise, simply haul and return times can be estimated based on the site conditions for on-site hauls or map traffic tools like Google Maps for off-site on-road hauls. So let's see an example of how we can model, analyze, and estimate the whole production rates. We would model the operation as a two-link system that depends on more than one resource, meaning the trucks and the loading equipment. We will study an example that involves a loader and a truck, and the truck payload is 10 cubic meters. The times of the whole cycle steps are shown on this activity sequence diagram. The big question here is, what's the productivity in cubic meter per hour of this operation? We'll analyze the whole operation production using a visual tool called multiple activity chart, which tracks the involvement of the different operation resources. Here we deal with equipment over time. The chart depicts the two main haul resources, one loader and one truck. The operation starts with the loading step, which involves both the loader and the truck. Then the truck goes on to haul, dump, and return back to another cycle. During the time the truck is in transit, the loader is sitting idle. Regardless, this loader truck cycle delivers a truck load every 10 minutes, which we call the operation cycle time. This extended multiple charts activity chart shows two cycles of the same operation. Now let's have a closer look to be able to derive some operational metrics from the chart. First, we can see that the loader's own cycle time is 3 minutes, assuming we have abundance of trucks ready to be loaded. Nevertheless, a single truck will have a cycle time of 10 minutes, assuming that the loader is always ready to load. This means for a single truck crew, the production is controlled by the single lonely truck. So the operation cycle time is the maximum of the durations of the disconnected cycles of the involved resources. We can calculate the utilization factors of the truck and loaders as the ratio between their disconnected cycle times and the operation cycle time. So the truck as a controlling resource will have a 100% utilization factor as it continuously works with no idle time. On the other hand, the loader is utilized only 30% of the operation time and cycle, as it is involved in only 3 minutes and stays idle for the remaining 7 minutes of the operation cycle. Finally, we calculate the operation production and productivity as the ratio between the work output over input. This translates to the ratio between the cycle work and cycle time. The cycle work is the amount of the soil hauled as the number of trucks times the truck capacity, which equals 1 cubic meters for this operation with only one truck. 10 cubic meters. So the productivity turns out to be 1 cubic meters per minute, which is the same as 60 cubic meters per hour. Another way to calculate the operation productivity is to calculate the unconstrained productivity of each resource and pick up the minimum to reflect the whole operation. The loader productivity is basically its loading rate of filling a truck every 3 minutes. On the other hand, the truck delivers a payload every 10 minutes, so the operation productivity is the minimum of both values, which turns out to be the truck productivity. In summary, the controlling resource in the operation with the longest cycle time and the least unconstrained productivity will set the pace for the whole crew and the operation. So what is the way to improve the productivity of this operation? Obviously, increase the number of trucks. So let's see the chart and productivity for 2 trucks. The loader fills the first truck, which moves on for its haul, dump, and return steps. Right after filling the first truck, the loader can fill the second truck, so it can also go on its own cycle. These 2 truck cycles will be repeated once the first truck gets back to the loader to be loaded again. So the operation cycle is marked with this zigzag shape, which means that the first cycle started before the second truck from the first cycle returned back. The cycle time of the loader is considered 6 minutes, which is the time it takes to load 2 trucks, assuming they are always available to be loaded. The truck cycle time is still the same. So the trucks are still controlling the operation due to their longer cycle time. But during the single cycle of the whole operation, the crew delivers 2 trucks payloads every 10 minutes. This means we double the productivity by doubling the number of trucks. You can also conclude that we improved the utilization of the loader from 30% to 60%, but it's still idle 4 minutes between loading the second truck and loading again the first truck. Let's see what's the case for using 3 trucks. Productivity keeps improving by increasing the loader's own cycle time to be 9 minutes, which refers to the time of repeating the loading of the 3 trucks, assuming their continuous availability. Trucks are still super busy and they still control the operation. However, the productivity is now calculated based on delivering 3 payloads for the same operation cycle time. Finally, the loader is also starting to be more utilized for 9 minutes out of the operation 10 minutes cycle. Let's keep the fun and add more trucks. The loader loads the first truck, which goes on its own journey for haul, dump, and return. The loaders fill the second truck, third truck, and fourth truck back to back. In the middle of the fourth truck loading, the first truck returned back and has to wait 2 minutes for the loader to finish. This means that the loader now became the super busy resource and controls the operation. This is shown by the loader's longer cycle time of 12 minutes, within which 4 truck payloads are delivered. So, the crew productivity is increased by adding a 4th truck, but not that much. It increased from 180 cubic meters per hour for 3 trucks to only 200 cubic meters per hour for 4 trucks. Also, the trucks now are underutilized, with them being idle 17% of the time. Let's prove a point here and increase the trucks to 5. We actually made things worse by getting the same productivity of 200 cubic meters per hour while reducing the truck utilization to 68. This means that we are paying an additional truck for no benefit. Let's plot all these crew configurations and see how the productivity changed with the increase of the trucks. Remember that our loader productivity is limited by 200 cubic meters per hour, which is the same as loading 1 truck every 3 minutes, or 5 trucks every 15 minutes. As we saw, 1 truck gives 60 cubic meters per hour, 2 trucks gives 120 cubic meters per hour, 3 trucks gives 180 cubic meters per hour, 4 trucks gives 200 cubic meters per hour, 240 cubic meters per hour. So it's a linear productivity increase with the addition of more trucks until we hit the ceiling of the loader productivity of 200 cubic meters per hour. We can see here a discontinuous relationship between the number of trucks and the productivity. And this discontinuity point is what we call the crew balance point. This point is the optimal crew composition where every resource is 100% utilized and achieving the maximum production of this serving resources, which is the loader. This point can be easily calculated by dividing the loader production over the truck production. So theoretically, we need 3.33 trucks to fully cover a single loader. Of course, we have to round up to 4 trucks if we want to have the loader 100% utilized, but the trucks will be slightly underutilized. What is the case if we want to increase the operation productivity beyond the 200 cubic meters loading rate of the loader? Add a second loader and double the maximum achievable production to 400 cubic meters per hour. Now your theoretical balance point is 6.67 trucks. The crew can be rounded up to 7 trucks to get 400 cubic meters and have the trucks underutilized. Or you can round them down to 6 trucks to get 360 cubic meters per hour and have the trucks fully utilized and the loader underutilized. So far we focus on productivity and the equipment utilization as the main metrics in comparing the different whole crew designs. I mean here by the whole crew design is the composition of the loading equipment and the hauling equipment. However, the true metric that should be the cost as it determines the competitiveness of the contractor, especially in hard bid projects. Cost performance here is basically the unit cost, which is calculated by dividing the operation crew hourly cost over the crew hourly productivity. In analyzing the hauling productivity, we decide on rounding up or down interim calculation results without really considering the impact on cost. For example, we can round the number of loader bucket up to have a full truckload or round it down to have a partial truckload. Also, we round the number of trucks around the crew balance point. So we should check the unit cost for every rounding case. This chart shows the unit cost change when considering fully loaded trucks, 6 loader buckets, or partially loaded trucks, 5 buckets. Also, we plot the different number of trucks for each loading case. We see that 13 partially loaded trucks is the best crew design as it results in the least unit cost. That's it for this lesson. Look for the accompanying exercise videos and enjoy your day reading.